Hi everyone, here's the last part of our kinetics, and we'll talk about the transition state theory. So we know what is activation energy, right? So effective collision between particles lead to the formation of a transition state or activated complex. So we have seen when that athlete was, jumping over the pole, we had seen that it's reaching to the activated complex and reaching for the transition state, right? So the transition state is unstable species, and that unstable complex can have partial bonds. They are not full bonds, they have partial bonds, and it is a transitional species part way between reactants and products. So because it is has partial bonds, normally we cannot isolate transition state. Okay. The transition state exists at the point of maximum potential energy. The energy required to form the transition state is the activation energy. Now let's look at this example where we have methyl bromide. BrCH3 is methyl bromide with hydroxide. What's going to happen is this hydroxide group is going to replace the bromide and it become next to the carbon. So the bromide will leave making Br minus, and then the OH will make a bond with the carbon and form methanol CH3OH. Now this is the transition state. So what need to happen? So you have a CH3, carbon with 3 hydrogens, carbon with 3 hydrogens. Bromine is still attached and oxygen wanting to attach to carbon. So oxygen is also making its way to carbon. So this carbon and bromine, this carbon and oxygen, they are not full bonds, they are partial bonds. Whereas these hydrogens, carbon, hydrogen, they are full bonds. You see here dash line indicating they are partial bonds. This is a full bond between oxygen and hydrogen. So the transition state contains partial bonds, which is dashed lines between carbon and bromine and between carbon and oxygen. And right now, since carbon has 1, 2, 3, 4, 5 bonds, it has a trigonal bipyramidal shape. Okay. Now this is how it look like. From the reactants to the transition state and to making the product. So the reactants are now the methyl bromide and hydroxide, they are separated. They are two separate molecules. Now the oxygen is reaching to carbon. You can see here oxygen is making its way to carbon, and then the carbon bromine bond become weaker. Okay, and then so this is a shorter bond, this is a longer bond because oxygen is trying to reach carbon and bromine is still attached to carbon. And then at the transition state, you can see they both have similar bond strengths, carbon oxygen and carbon bromine. And then after the transition state, so this is the activation energy, or this complex is a transitional state or the activated complex. After the transition state, what's going to happen is the carbon bromine bond will become weaker and carbon oxygen bond will become stronger and shorter. So this become elongated. And then bromine has to leave. So the bromine will fall apart. And then final product, we will have a bromide molecule separate and methyl CH carbon attached to oxygen as methanol. Okay, so this is the depiction of a reaction progress between methyl bromide and hydroxide. Okay, for many of the reactions, this is how it's happening, and you can also see the molecular diagram showing it here. Okay. Now, some of these reactions, you can have exothermic reaction or endothermic reaction, it doesn't matter, but each and every kind need to reach the activated complex or the transition state, have to overcome the activation energy barrier and then form the product. So this one is NOCl becoming NO and chlorine. So this is going to be a reactant NOCl. So this is NOCl. So this is the activation energy. So at the transition state, nitrogen, oxygen, so the chlorine and nitrogen monoxide and the chlorine need to be separated. So you can see here the weaker bonds. And then once the transition state reaches, it become the products. So the products that we need to form will be formed, nitrogen monoxide and chlorine. So this is the activation energy for the forward reaction, and this is the activation energy for the reverse reaction. And this is the delta H, enthalpy change. And this is a endothermic reaction because products has more energy compared to the reactants. And another reaction, NO plus ozone. Forward reaction transition state, activation energy, and this is the activation energy for the reverse reaction. And this is exothermic reaction because the products have lower energy compared to the reactants. And this is the delta H. Reaction mechanisms. So the mechanism of a reaction is a sequence of single reaction steps that make up the overall equation. Now sometimes we will have one particular reaction, but some reactions have several steps. So the whole reaction consists of many different individual steps. Okay, so the individual steps of the reaction mechanisms are called elementary steps because each one describes a single molecular event. Each elementary step is characterized by its molecularity, the number of particles involved in the reaction. The rate law for an elementary step can be deduced from the reaction stoichiometry. Reaction order equals molecularity for an elementary step only. Remember, we talked about the reaction orders before, but we said molecularity is the stoichiometry or the molar ratio. Normally, molar ratios and the reaction orders are not the same. But if you have elementary steps, meaning these elementary steps give you the overall reaction, elementary steps molar ratios can be considered as the reaction order for that particular reaction only. Okay. If you have elementary step A goes to product, we call this as a unimolecular reaction because it is 1 mole, 1A. Normally we don't write 1. So we can write the rate law, rate equals K is rate constant times A. Now if you have a 2A in elementary step, now the stoichiometry or the molecularity is 2, molar ratio is 2, we call it as a bimolecular reaction. Rate is K, A raised to the power 2. Remember, this is for the elementary step, not for the overall reaction. Now if you have A plus B, 1 to 1 ratio, there are 2 molecules and we say it's a bimolecular reaction, and then the rate is with respect to A first order, with respect to B first order, molecularity bimolecular because there are 2 molecules. Now this one 2A plus B, 2 plus 1 3, right? So this is termolecular and the rate law would be second order with respect to A, first order is with respect to B. So we can, for these elementary steps, by looking at the molar ratio, we can deduce the molecularity. But if it is the overall reaction, remember, we did not say like that. So M and N reaction orders we had to calculate from the experimental data. We could not directly get it from the stoichiometry or the molar ratios. Okay, so this is only for the elementary steps. The following elementary steps are proposed for a reaction mechanism. Chlorine Cl2 goes to 2Cl, and then chlorine plus CHCl3 giving you HCl-CCl3, and then chlorine plus CCl3 giving you CCl4. Write the balanced equation for the overall reaction. To find the overall reaction, so there are 3 elementary steps. You add these 3 together, and then if there is anything that can be cancelled, it will get cancelled. So to get the balanced equation for the overall reaction, determine the molecularity of each step, write the rate law for each step. Now let's look at the molecularity of each step. Now for the first one, 1 mole of Cl2 giving you 2 moles of Cl. What is the molecularity of this reaction? So this step, it's unimolecular, right? So we have to write the rate law for this one. If you write the rate law, that would be K equals, not the K, rate equals. Okay, so rate equals K, since it's unimolecular, Cl2. That would be the rate for the first one. What about the second one? Second one rate would be K. We have 2 molecules chlorine and CHCl3. What is the molecularity? What is the determine the molecularity of each step? So for the first one, it's unimolecular. What about the second one? There are 2 molecules, one chlorine, one CHCl3, so it's bimolecular. What about the last one? One molecule here, one molecule here, so that is also bimolecular. Molecularity of each step. Unimolecular, bimolecular, bimolecular. Right? And then the rate law would be for the last one, K, Cl, first order, CCl3, first order. That's the rate for the third one. Okay, we did B and C. Now write the balanced equation. To write the balanced equation, what we do is we're going to add these 1, 2, 3 equations together. 1, 2, 3. So when you add it up, we have 1 chlorine, so you write it down here. Everything you have in the reactant side you would add up, and then after the arrow you have products you write in one side. So 1 chlorine, and then there is 1 Cl here, another Cl here, this Cl right there, and CHCl3, this chlorine, CCl3, and the product sides we have 2 Cl, another HCl, CCl3, CCl4. And then we're going to see what are the common ones in the both sides. So there is a 1 chlorine, 2 chlorine, 2 chlorine that get cancelled. And CCl3 on the reactant side, CCl3 on the product side, they get cancelled. So what is left is chlorine, CHCl3, and then the product side we have HCl and CCl4. So that is the balanced equation. And these are the rate laws which we did together. And then we also talk about the molecularity. Unimolecular, bimolecular, bimolecular. Okay. Now when you have several elementary steps, we don't know which one is going to be the rate determining step. Some of these could be fast reaction, some of these could be slow reaction. So whichever one would be the slow reaction is going to be the rate determining step. The slowest step in a reaction is the rate determining or rate limiting step. In this reaction, NO2 with carbon monoxide giving you NO and carbon dioxide has been proposed to occur by two-step mechanism. First mechanism, NO2, two NO2 molecules giving you NO3 and NO2, and this was found to be the slow reaction and also going to be the rate determining step. And the second reaction is fast. So the observed rate law is rate equals K with respect to NO2 second order, which also aligns with the slow mechanism or the slow reaction. So the rate law for the rate determining step becomes the rate law for the overall reaction. Okay. So here's a reaction energy diagram for the two-step reaction of NO2 and fluorine and NO and oxygen. There are two steps. So it's the first step is NO2 and fluorine. You need certain activation energy to become the transition state, and then it will first become NO2F plus fluorine plus NO2. So we have not come to the product yet. So there are two steps. So this is the first step. And then the second step again also have a activation energy. That is fast. because activation energy is small, and this need more activation energy, so it's a slow step. And then the second, after the second activation energy, you get the product. So this is the fast one, this is the slow activation energy. So the rate will be determined by this step. Okay, and in this one here, the first step is a fast step and it needs a small amount of activation energy. Second step, from here to here, is activation energy. It need more activation energy. It's a slow step, so that is the rate determining step. Each step in a multi-step reaction has its own transition state, which occurs at the energy maximum for that step. So sometimes we can use a catalyst to speed up a reaction. So what is a catalyst? A catalyst is a substance that increases the reaction rate without itself being consumed in the reaction. In general, catalyst provides an alternative reaction pathway that has a lower total activation energy than the uncatalyzed reaction. Catalyst will speed up both the forward and the reverse reactions, and it does not affect either delta H or the overall yield for a reaction. So this diagram shows us how a catalyst would speed up a reaction. So the orange color one is the uncatalyzed reaction. It needs a larger activation energy, you see, without the catalyst. But with the catalyst, it might take a different path, but it would give you the same product. It would alter the path. See, it would give you an alternative reaction pathway that has a lower total activation energy than the uncatalyzed reaction. Catalyzed will lower the activation energy by alternating the pathway. Okay. Here's an example of a catalyzed reaction. All of you guys have taken General Chemistry 1, and we did one experiment where we decompose hydrogen peroxide with potassium iodide. So potassium iodide there was the catalyst to accelerate or speed up or catalyze the decomposition of hydrogen peroxide. Small amount of, we added potassium bromide, sodium potassium, they are in the same group, so it should be similar. Added to a solution of H2O2. Oxygen gas forms quickly as bromide catalyzes the H2O2 decomposition. The intermediate bromine turns the solution orange. The solution becomes colorless when the bromine is consumed in the final step of the mechanism. If there was another step, but we didn't do a second step when we did our hydrogen peroxide decomposition in General Chemistry 1, but we saw the bubbling of oxygen and decomposition of hydrogen peroxide. Right? Okay, so that concludes our first chapter on kinetics.